Hi, everyone, and welcome to this next installment in my Algebra and Precalculus video series. In this video, we're going to be talking about solving equations, something we've talked about previously, but in this video, specifically exponential and logarithmic equations. So what is an exponential equation? What is a logarithmic equation? Well, basically, any equation where your variable, and I'm going to be using x as the variable. I'm not going to do anything fancy. So any equation where x appears as an exponent, we call that an exponential equation. And anywhere where any equation where x appears in a logarithm, we call that a logarithmic equation. In this video, I'm going to be doing 10 or 11 equations. This is a lot of variation, so I want to make sure I'm hitting at least most of the main types. On this next slide, I'm going to give just a list of all the equations we're going to be working through. So I have them numbered 1 through 5, so 1a, 1b, 1c. They're all similar types, and 2a, 2b, 3, and so on. So you see some of these equations, your variable x is an exponent, 1a, 1b, 1c, 2a, 2b, right? So we've got some exponential equations, right? These are exponential equations, and the rest are logarithmic equations. X is part of a logarithm. All right, now, if you haven't watched the video directly before this one, you might want to pause this one and go back to that one, because I'm not really teaching anything new in this video. In the previous video, we filled our toolbox with all the various tools we're going to need. Our properties of logarithms, our rules of logarithms, rules of exponents. And in this video, we're just going to apply those. So everything from the previous video is a tool we're going to use to solve these equations. So let's just review a couple of really sort of important things in the context of solving these equations. So keep in mind, there are three things to remember. One, definition of a logarithm. All right, so talked about that in the previous video. Extremely important. Can't do a lot of these without the definition of the logarithm. And another thing that I discussed previously is that these exponential functions and logarithmic functions are inverses of each other. So exponential, logarithms, these guys are inverses of each other. Now, not all functions have inverses. These guys do. Exponential functions have inverses. They are logarithms, vice versa. So for a function to have an inverse, which not all functions do, but for a function to have an inverse, they have to be 1-to-1, right? So we know exponential functions are 1-to-1 because they have inverses, right? So the way we're going to apply this fact, exponential functions are 1-to-1. Okay, great. What does that get us? Well, this property right here, right? If b to the m is b to the n, so if you have the same base, b to this is equal to b to that, the exponents have to be equal. And then the inverse of the exponential functions are the logarithms, so logarithmic functions are also 1-to-1. Right, so we've got the definition. We've got exponential functions are 1-to-1, and we've got logarithmic functions are 1-to-1. So on that previous slide, where I had all 11 problems, 11 or 12 problems, however many there are, every one of those problems is going to be solved using one of these three statements. One of these three statements. Either the definition of the logarithm, the result of exponential functions being 1-to-1, or logarithmic functions being 1-to-1. All right, so let's go through. We'll just go through slide by slide. Each slide will be one equation. We'll talk about how to approach it, how to set it up, why we set it up the way we do, what are some options. Sometimes many times there's more than one way to solve a problem. Okay, so keep these in mind as we're going through these equations. And also keep in mind our properties of logarithms. All right, so we talked about expanding and condensing logarithms. Actually, all three of these were used in that context. And then some specific results of just the definition of the logarithm. So again, these are all things. These are all things I talked about and explained in my previous video, the video right before this one. In this video, now we're just using these tools. All right. So we've got these three statements here. We've got some rules. We also have some rules of exponents. All right, so let's get into it. Let's get into it. So number one, solve the exponential equation by expressing each side as a power of the same base. Expressing each side as a power of the same base. Well, we see the number 8 and we see the number 32. And the numbers 8 and 32 have something in common. They're both powers of 2. 2 times 2 is 4, times 2 is 8. So 2 to the third power is 8. And then 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So if you got 5 2s, 2 to the fifth power, you got 32. So we could replace each of those numbers. We could replace each of those numbers, the 8 and the 32, with a power of 2. So instead of 8 to the 3x, we've got 2 cubed to the 3x. And instead of 32, we've got 2 to the fifth power. All right, and then if you look at the left-hand side of the equation that I just wrote in blue, 2 to the third power in parentheses and then raised to the 3x power, well, we have one of our rules of exponents. When you have a power to a power, when you have a power raised to another power, you multiply those exponents. So that's 2 to the power of 3 times 3x. 3 times 3x is 9x, so that's 2 to the power of 9x is equal to 2 to the fifth power. Okay, and now this 2 to the 9x equals 2 to the fifth. I'm going to go back a couple of slides. Looks just like this. Same base on both sides. We have 2 to a power equals 2 to a power. So then the exponents have to be equal. So that means, and this is a result of the exponential function being 1 to 1, if 2 to the 9x is equal to 2 to the fifth, then the 9x has to be equal to 5. And solving for x means getting rid of the 9, the times 9, which we could do by dividing by 9. Divide both sides by 9. And we've got x is equal to, so those 9s cancel, x is equal to 5 over 9. It's only possible to solve this way because we're able to take both sides of the equation and write them as an exponent of the same base. 2 to a power equals 2 to a power. Okay, 1b. 1b is similar. Very similar. So we've got the number 125 and we've got the number 5. All right. So 125, well, 5 times 5 is 25, times 5 again is 125. So 125 is 5 to the third power. And then we have a property of exponents. A negative exponent means reciprocal. So if 125 is 5 to the third, then 1 over 125 is equal to 5 to the negative third. All right, so we'll use this on the left side. And then on the right, the square root of 5. Well, another way of writing the square root is the 1/2 power. So the square root of 5 is the same as 5 to the 1/2 power. All right, so this we'll use on the right-hand side. So let's rewrite that equation. Instead of 1, instead of 1 over 125 to the x, we could say that's 5 to the negative third power raised to the x. And then on the right, instead of the square root of 5, we could say 5 to the 1/2 power. Right, the left-hand side, again, we have a power raised to a power, so we can multiply those exponents. That's 5 to the negative 3x is equal to 5 to the power of 1/2. So if 5 to the negative 3x is equal to 5 to the power of 1/2, well, then negative 3x, the exponent on the left, has to equal 1/2 the exponent on the right. All right, solve for x. We've got negative 3 times x, so let's divide by negative 3 both sides. So those negative 3's cancel. We get x is equal to, well, 1/2 divided by negative 3. I think that's going to be a negative 1 over 6. Negative 1 over 6. So just like off, it's a little scrap work off to the side. 1/2 over negative 3 is 1/2 divided by negative 3. Negative 3 over 1, which is 1/2 multiplied by negative 1 over 3, which is negative 1 over 6. So that's one way of looking at it. And feel free to use the calculator as well. Feel free to use the calculator. So we could take 1/2, divide by negative 3 equals, and then don't forget math 1. Math 1 takes our answer, which is the decimal, math 1, and converts it to a fraction. And so there's negative 1 over 6. So whether you do it by hand, paper, and pencil, calculator, it doesn't matter. We get negative 1 over 6. Okay, I'm going to go back one slide. Back one slide. It's right here. 8 to the power of 3x equals 32. Well, we were able to solve this problem using the one-to-one property, actually not of logarithms, but of exponents, exponential functions, because 8 and 32 are both powers of the same number. So what if instead of an 8, we had a 9? What if instead of 8, we had a 9? Right? So now there's a problem. 9 is a power of 3. That's 3 squared. 32 is a power of 2. That's 2 to the 5th. So now we can't take the same approach here. We can't take both sides and write them as powers of the same number. And here we said 8 to the 3x, we got 2 to the power of 9x is equal to 2 to the 5th. That's how we solved this one a minute or two ago. Well, over here, in this problem, we can't do that. All right, so what do we do? Well, the most fundamental rule, the most important rule in algebra, the most important rule in algebra for solving equations. Whatever you do to one side, you have to do to the other. Right? You can do whatever you want to one side as long as you do the same thing to the other side. So what I'm going to do here is take the log of both sides of the equation. Now, when I say log, I use natural log. I always use natural log. You could use common log, either one. You could use any log you want. You could take the log base 6 of both sides, but that's not really helpful because on the calculator, you've got these two buttons. You've got one button for the log base 10. If you look at the left side of the calculator, and this is not, not just the TI-84, but any calculator, any scientific calculator, generally there's going to be a button for log, common log, LOG, and natural log, LN. So those are the two logs you want to use as tools, right? Because those are the ones that appear on the calculator. So my general rule of thumb is I always use the natural log if I'm going to apply the log of both sides of an equation, unless the equation has a 10 in it, power of 10 in it. Then I'll use the common log. Okay, why? Why am I doing this? Why am I taking this original equation, the 9 to the 3x is equal to 32, and why am I taking the log of both sides of the equation? Well, we've got a rule of logarithms that says the log base b of a to the c is equal to c times the log base b of a. All right, we want to solve for x. That's our goal. We want to solve for x. In the original problem, x is an exponent. We got to bring it down. We got to bring that exponent down. And we have this rule of logarithms. That says when you have the log of something to a power, that power pops out front as a multiple. And that allows us to bring exponents down. All right, so the next step would be, this is the natural log of 9 with the 3x out front. So we bring the log into the equation because we have a property of logs that says when you have an exponent in your argument, that exponent comes out front as a constant multiple. All right, so once we put this log out front, we have to do the same thing to both sides. We don't need it on the right. We don't need a log there, but we have to do the same thing to both sides. So once we have that log, then we're able to take that exponent, pop it out front. So then the variable x is no longer an exponent. Right? Now we want to solve for x, right? This is a number, 3. This is a number, ln of 9. I don't know what that number is. Maybe 2 point something. I don't know, 1 point something. This is a number as well. Right? So all we care about is this. It's a multiplication. Right? How do you get rid of multiplication? You divide. So x is being multiplied by 3. So divide both sides by 3. That'll cancel off that 3. X is also being multiplied by ln of 9. So also multiply or divide both sides by ln of 9. So those will cancel. And the only thing left on the left-hand side is x. And on the right, we get the natural log of 32 divided by 3 times the natural log of 9. What is that? Like, what is natural log of 32 divided by 3 times the natural log of 9? I have no idea. I have no idea. That's what calculators are for, right? So this, let me put a little green circle around this guy. This is the exact answer. This is the exact answer. Now, if you want a decimal approximation, if you want to, approximately what is that? Round it to a couple of decimal places. We could bring over the calculator. And we can say natural log of 32. And we could divide that. I'm going to put it in parentheses. So both the 3 and the ln of 9 are on the bottom. So parentheses 3 times the natural log of 9, close parentheses, close the other parentheses. And so it's about 0.526. So approximately, if we round it to 3 places, let's say it's approximately 0.526. All right, so we got the exact answer. We got the decimal approximation. All right, so let's move on. I mean, these problems are all, big picture approach is more or less the same. We want to solve either an equation where either the variable is an exponent or the variable is part of a logarithm. And in this one, the directions explicitly state to do what we just did in the last problem. Express the exact solution in terms of natural logs or common logs. And then use a calculator to obtain a decimal approximation. Now, I don't say exactly how many places to round to. When you're doing the homework, the directions will be more specific, round to 3 places or round to 4 places, either way. Okay, so we got 5. E to the x is equal to 31. 5e to the x is equal to 31. Well, I think it might be easier if that 5 wasn't there. If we just had e to the x on one side. And the reason I say that, it's not just random. The reason I say that is because the natural log of e to the x, the natural log of e to the x is equal to x. Right, so this is a property we've seen, and this is a property that I explained in my previous video, the video right before this one. Why? Why is the natural log of e to the x equal to x? Well, when we write ln for natural log, what we literally mean is log base e. Right? You'll never see it written this way in a book. But that's what we mean. We write ln, but ln, the letters ln, natural log, means log base e. So when you have log base e of e to the x, well, that's a log and an exponential function. They cancel out each other. They're inverses. So that's equal to x. So because of this property, that tells me I want to get rid of that 5. I'm going to take the log of both sides, the natural log of both sides. But first, I'm going to divide by 5. Get the 5 over there. So we got e to the x is equal to 31 over 5. Now we can take the log of both sides. Now I know it's natural log, but I use natural log for everything. So I shorthand it. I just call it log. So I'm saying log both sides, but yes, it's the natural log of both sides specifically. All right, so on the left, we got natural log of e to the x, which is x. And that's equal to the natural log of 31 over 5. And that's our answer. Once we have x by itself, we've solved the equation. So what is the natural log of 31 over 5? Again, I have no idea. I need a calculator for that. Natural log 31 divide by 5. Yeah, it's about 1.8, 1.82, 1.825, depending on how many decimal places you need to round to. All right, moving on. That was 2A. 2B, similar problem. Well, this one's actually we could take the log immediately in this one because there's no multiple out front. So we've got e to the 1 minus 4x is equal to 943. And what I'm going to do is take the natural log of both sides of this equation. Right? The log base e and the exponential base e, they cancel. And we've got 1 minus 4x is equal to the natural log of 943. Who knows what that is? Calculator will tell us. All right, we got to solve for x. We got to solve for x. So we could minus 1 from both sides, right? We have a positive 1 in blue, so we could cancel that off with that minus 1. So that's a negative or a minus 4x is equal to, please don't make this mistake. Don't say the natural log of 942. You cannot do that, right? You can't subtract 943 minus 1. This is not the number 943. That 943 is part of this natural log. So this is one number. You can't just ignore the ln and treat that like it's a 943. Can't do that. Right? The natural log of 943 minus 1 is the natural log of 943 minus 1. Right? You can't combine those two. All right, one more step. We got to get rid of the minus 4 in front of the x, so we'll divide both sides by minus 4. On the left, those minus 4s cancel. We've got x is equal to natural log 943 minus 1 divided by negative 4. Well, technically, to consider our answer in simplified form, can't leave a negative sign on the bottom of a fraction. So if we take that negative sign from the bottom and move it up top, It's still a negative sign. Whether it's on top or bottom, doesn't matter. You could say negative a over b is the same as a over negative b, which is the same as negative a over b. It depends on the context, but this one in the middle, negative on the bottom, that's not simplified. Right, not simplified. So we put the negative sign on top. And that's the negative of natural log of 943 minus 1. And that negative will actually change the order of this difference. So that'll actually be 1 minus the natural log of 943 all divided by 4. And I think that's simplest answer, meaning using the least number of symbols. And we could again get a decimal approximation of that. Let's clear this out. 1, I'm using parentheses around the numerator, just so the calculator does things in the right order. 1 minus the natural log of 943. Close those parentheses, close those parentheses. Divide by 4, so it looks like about a negative 1.46, thereabouts, depending on how many places you want to round to. All right, looking good. Looking good. Moving on. So now number 3. Solve the following logarithmic equation. And also, I don't want to breeze past this part. Be sure to reject any value of x that is not in the domain of the original logarithmic expression. And what does that mean? What does that even mean? You cannot, you absolutely cannot take the log of a negative number or 0 or of 0. Right? So the thing inside, the argument of the logarithm, this has to be positive. Right? It has to be positive. So if we work through this problem, we go through some steps and we get x equals negative 5. Well, if we get x equals negative 5, I don't think that's the answer we're going to get. But if we did get negative 5, well, if you plug a negative 5 in for x, that gives you a negative in here. So we would say no solution, right? We would say no solution, right? So your final answer cannot break any mathematical rule. Previously, we've seen rules like you can't divide by 0. You can't take the square root of negative numbers. Well, now, another rule to add to the list, you can't take the log of a negative number or of 0. All right, don't want to spend too much time on this. Talked about it in the previous video, the one right before this one. All right, so what does this problem look like? What does this original problem here look like? Well, to me, it looks like the definition of the logarithm. The log base b of a is equal to c means the same thing as b to the power of c is equal to a. When you have this, you can rewrite it as this. That is the definition of the logarithm. Those two statements mean the same thing. I like to sort of visualize this as the scorpion tail. That's the method I like, right? Scorpion tail. So start with the base, the 3. The 3 raised to the power of -2 is equal to x plus 3. All right, 3 to the power of -2 is equal to x plus 3. The original problem is in logarithmic form. Using the definition of the logarithm, we've rewritten it into exponential form. Exponential form, a whole lot easier to deal with. If you want to solve for x, all you got to do is -3 from both sides. Get x by itself. What is 3 to the -2 power? Well, that's 1 over 3 to the +2 power, or 1 over 9. Feel free to use the calculator if you're more comfortable. Right, so we have an exponent key, this caret right here on the right. So we could say 3 to the power of -2. All right, problem, you can't use decimals. If the decimal involves rounding, you cannot change a fraction to a decimal if it involves rounding. But luckily we have math 1, convert our answer back to a fraction, and there's the 1 over 9. So up to you. Use your, paper and pencil, do it in your head, do it on the calculator. 3 to the -2 power is 1 over 9. Solve for x, we got a -3 from both sides, and that's it. X is by itself. X on the right. So now we got 1/9 minus 3. It's actually going to be -26 over 9. Right? 1 over 9 minus 3 is 1 over 9 minus 3 over 1. Get a common denominator. 1 over 9 minus 27 over 9. 1 minus 27 is -26. So -26 over 9. If you use the calculator, we've already got 1/9 in there. So as soon as we hit the minus key, it's going to take previous answer, which was 1/9, minus 3. And there's the 26 over 9, -26 over 9. So either way, whichever way you're more comfortable with, our final answer is -26 over 9. Now that's smaller than 3. So if we plug that in for x, into the original problem, in that original logarithm, that doesn't give us a negative. So -26 over 9 plus 3 is a positive number. Right, so that's fine. If we take this and put it in for x, we're good. Doesn't give us a negative under the square root. So we get to circle it in green. There's our answer. All right, 3B. 3B, similar problem. I'll go through this one a little bit quicker because it's the same problem, just different numbers. 2 to the power of 6 is equal to 8 plus, or 8x plus 6. 8x plus 6. 2 to the power of 6 is equal to 8x plus 2. 2 to the 6th power. That's 2 times 2 times 2 times 2 times 2 times 2, which is 64. We got 64 is equal to 8x plus 2. We want to solve for x. We could subtract 2 from both sides of this equation. That 62 is equal to 8x. Divide both sides by 8. We'll get x by itself. We got x is equal to 62 over 8. That's going to be 31 over 4. That works because 31 over 4 is positive. So if we plug that in up here, 8 times a positive number plus 2 is still going to be positive. So that's fine. 31 over 4. All right, almost done. Almost done. We just have 4 more to go. Well, actually 2 problems, but 2 versions of each one. Okay, so now for the first time, we see a problem that has multiple logarithms in it. Multiple logarithms. We got 2 logarithms here. Now, actually, I'm gonna go back to the very beginning. The very beginning, second slide. Okay, so the last 4 problems. Right, I'm on this one right now, 4A. But the last 4 problems all have multiple logarithms. 4A has 2, 4B has 2, 5A has 3 logarithms, 5B has 3 logarithms. So there's 2 different ways to approach these problems. And you can't always use both methods. It's either one or the other. So there's the definition. So this is like option 1. It's the definition of the logarithm. I'll just say definition of the log. Definition of the logarithm. The definition is the log base b of a to the c. Sorry, the log base b of x is equal to c. Means the same thing as b to the power of c is equal to x. Well, in this definition, if you look at the left-hand side, there's a c, there's a number, right? A constant that doesn't have a logarithm attached to it. So if you're going to use the definition of the logarithm, you have to have a standalone number somewhere in the equation that's not part of a logarithm. So if you look at 4a, you've got the number 4 by itself. If you look at 4b, you've got a +1, so there's a 1 by itself. So we could use the definition of the logarithm in 4a and 4b. For the 2 problems in number 5, 5a and 5b, we cannot. We cannot use the definition of the logarithm because there is no standalone constant that's not attached to a logarithm. So in 5A and 5b, we've got a log is equal to a log plus another log. Actually, both of them same. All right, so if the definition is not going to work there, the second option, the one-to-one property. So if the log of m is equal to the log of n, then m has to equal n. M and n this is, m, and well, yeah, we have too many logs here, so we're gonna have to do a little work first. All right, so let's go back to the individual problems one by one. These last 4, see how they play out. Okay, when I see this, there's multiple logarithms, but I see a number by itself. So that tells me I'm thinking, use the definition of the logarithm. Yeah, okay. It also says it up here, but you're not going to see that statement in red. You're not going to see that in the homework. Right? The problem is not going to say solve the equation and use the definition of the logarithm to do so. It's just going to say solve the equation. That's all. Solve the equation. It's up to you to decide whether to use the definition or the one-to-one property. It's one or the other. The definition of the logarithm, and I'll write it down one more time. The log base b of a log, well, let me use the the specific letters I use in the definition doesn't matter. All right, but I'm going to go back to the ABC. That's what I used earlier in this video. What's important is that the correct numbers go in the right places when you convert it to exponential form. When you convert it to exponential form. So b to the power of c is equal to a. All right, but what's important here is using the definition. You got one logarithm. And you've got one number. All right, one log and one number. In this problem, we have two logs and one number. All right, so what do we got to do? We've got to condense. We've got to condense those logarithms. So let's focus in on the left-hand side of the equation. And we have a rule. We have a rule of logarithms that says, let me go back to blue, the log of m minus the log of n is equal to the log of m over n. And this is one of those rules that I think it's on the second or third slide back at the beginning of this video. There's a rule for addition and multiplication. There's a rule for subtraction and division. In this case, we've got a log minus a log. So let's use this rule. So the left-hand side of the equation becomes the log base 2 of x plus 12 over x minus 3 is equal to 4. All right, so now we got the log of something is equal to a number. This looks like the definition of the logarithm to me. So 2 to the power of 4 is equal to that fraction. 2 to the power of 4 is equal to x plus 12 over x minus 3. 2 to the 4th power, well, that's 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So 4 2's give you 16. And that's equal to x plus 12 over x minus 3. I see a fraction, I want to get rid of it. That's my instinct, always. See a fraction in an equation, get rid of it. We could get rid of a fraction always by multiplying by the denominator. So if we're dividing by x minus 3, let's multiply by x minus 3. All right, multiplying and dividing cancel each other off. Whatever you do to one side, you got to do to the other side. So on the right, we've canceled off the bottom. We've got x plus 12. And on the left, the 16 is being multiplied by x minus 3. So we got to do x times 16 and a minus 3 times 16. So that's 16x minus 48. 16x minus 48. Let's bring this over here. So I got a little bit more room. 16x minus 48 is equal to x plus 12. It's no longer an exponential or logarithmic equation. It's a linear equation. And we've seen this plenty of times. Get all your x's to one side, get all your numbers to the other side. So I'm going to start by minusing x from both sides, so they cancel the x's on the right. So now we've got, let's see, 16x minus x, that would be 15x minus 48 is equal to 12. We can add 48 to both sides. That'll cancel those 48s on the left. Well, we've got 15x is equal to 60. 15x is equal to 60. Divide both sides by 15. Right, those 15s cancel. And it looks like we've got x is equal to 60 over 15, which will be 4. X is equal to 4. If we put 4 into our original problem, we don't get any negatives inside of the logarithms. So this checks out. This checks out. All right, so 4b, a similar problem, just some different numbers. We got 2 logs, 1 number. All right, that's it, 2 logs, 1 number. So let's see, where can we start here? Well, the first thing I see, we got 2 times the log base 7 of x plus 3 is equal to the log base 7 of 7 plus 1. Well, let's start with this. What is the log base 7 of 7? That's actually equal to 1. We've got one of our properties of logarithms. Again, this is going back to that table of rules on the third slide, second or third slide. That says when you take the log base b of b, where those two numbers are the same, like log base 7 of 7, that's equal to 1. Because 7 to the first power equals 7. So the exponent is 1. Right, so we got 2 times the log base 7 of x plus 3 is equal to 2. This almost looks like the definition of the logarithm, but the problem is got this 2 out front. Got to get rid of that 2. And if you're going to use the definition of the logarithm, 7 to the power of 2 is equal to this, there can't be a 2 out front. And it's the log of something equals something. That's the definition of the logarithm. So get rid of the 2. I'm going to write this twice, and I'm going to write it over here in black. 2 log base 7 of x plus 3 is equal to 2. Now let's do this a couple of different ways. I mean, there's almost always some variations in how you can get through the steps of a problem. So the blue version on the left, we've got another rule of logarithms that applies, and that's the log base b of x. Well, I'm going to drop the base b. It could be any base. We know that. The log of x to the c is equal to c times the log of x. All right, so exponent could pop out front, or a multiple out front could pop up as an exponent. So that rule is saying this 2 out front, we can move it up here as an exponent. All right, that gets rid of the 2. So we'll have log base 7 of x plus 3 to the second power is equal to 2. And now we could use the definition of the logarithm. 7 to the power of 2 is equal to the argument x plus 3 squared. 7 to the power of 2 is equal to x plus 3 squared. And 7 to the power of 2, we know that's 49. If we want to solve for x, we could multiply everything out, move everything to one side, get a 0 on one side, factor. We could take that route. But I think it's easier if we just square root both sides. All right, square root the left, square root the right. Just be careful with the square roots. When you take the square root of an equation, one side gets a plus minus. One side gets a plus minus. So this is actually 2 equations. One with a positive 7, one with a negative 7. So we got 7 equals x plus 3. We got minus 7 is equal to x plus 3. Subtract 3 from both sides. That'll give us 4 is equal to, oh, it doesn't like me writing so close to the bottom here. Let me move this over. All right, so this is 2 equations. Let's do it this way. 7 equals x plus 3, and negative 7 equals x plus 3. Minus 3 from both sides. The first one will give us 4 is equal to x. One answer. Okay. And the other one, minus 3 from both sides, we'll get negative 10 is equal to x. There's our second answer. Sometimes you get 2 answers. Sometimes you get 2 answers. This is not one of those times. Because you always got to check your final answers. If you plug them back in for x, does it cause any issues? Well, we're actually plugging the answers in for x right here. So if we put in a 4 for x, we get a positive number. 4 plus 3 is 7. No problem. But if we plug in a negative 10 for x, negative 10 plus 3 is a negative number. So that one does not work. So only one of these solutions work. You always have to just make sure your final answer, if you were to plug it back into the original equation, it doesn't give you a negative number or a 0 inside of a logarithm. Okay, and I think this was a little bit more work than we needed to do. I'm going to go back to the original, what I have written in black over here, the 2 log base 7 of x plus 3 equals 2. And I think we could, either way, we got to get rid of the 2. We can divide by 2. It's another method. So we get the log base 7 of x plus 3 is equal to 1. We're still taking the same approach. Definition: 7 to the power of 1 is equal to x plus 3. 7 to the power of 1 is equal to x plus 3. But in this case, if you do it this way, minus 3 from both sides, you only get that one answer. X is equal to 4. All right, so the reason I did this both ways, one way is a little bit more, like the blue way is a little bit more complicated. Not terrible. But you don't have to always pick the shortest way. Like that's not the most important thing at this stage. What's important is we're all getting to the same final results. So if you do it the first method I used, using the log rule, if you use the second method, dividing by 2, either way, we get to x equals 4. Okay, so that's equations. These last two problems, the equation has multiple log terms. This one had 2 logs and 1 number. This one had a plus 1. The one before it had an equals 4. So let's move on to the last problem. This one will be a bit quicker. We've got a log is equal to a log plus another log, right? There's no number on its own. So we're not going to use the definition. We're going to use the one-to-one property of logs, which is saying if the log of m is equal to the log, write that a little neater, the log of n, then m has got to be equal to n. So you want a log, like 2 log, a log on the left, log on the right. We're good on the left-hand side. We have the log of x plus 11. So we could look at the right-hand side and we can combine those, right? We could condense those 2 logarithms. It's important that you either have these rules memorized or you have them written down next to you when you're trying to solve these equations. So you can't solve these equations without these tools, these log rules. So the log of m plus the log of n is equal to the log of m times n. Right, so that's one of those rules on that list at the very beginning of the slideshow. So these 2 logs come together. We've got the log of x plus 11 is equal to the log of x times 11. And so we're basically doing a little loop here. Right, based on this rule right here. We went from step 1 to our original problem to the next step. Then we're using the one-to-one property, which when we have a single logarithm on the left, a single logarithm on the right, essentially it allows us to cancel. So we've got x plus 11 is equal to 11x. Right, when you have a single logarithm on each side of your equation, you can essentially cancel the logs. So now we're just a couple steps away. Let's get the x's to one side. So we'll cancel that x on the left. 11 is equal to, looks like we've got 10x on the right. Divide both sides by 10. We got x is equal to 11 over 10. All right, let's do one more. It's almost the same as this one, but trust me, it's going to be a little bit different. Let's just work through it and see how it shakes out. Right. Almost the same as the last problem. Log is equal to log plus log. And we've got two logs on one side, one log on the other. And we'll do this problem the same way. We could condense these into two, or condense these two logs into one. So we'll have ln 5x minus 7 is equal to ln of, we got to multiply, x plus 2 times 6. So it'll be 6x plus 12. And we're multiplying x plus 2 and 6, combining them into one logarithm. This becomes this. Now we've got a single logarithm on the left. We've got a single logarithm on the right. And again, speaking a little bit informally, but it allows us to cancel the logs. And this is a result of the logarithmic function being 1 to 1. So 5x minus 7 is equal to 6x minus plus 12. Solve for x. It's no longer a logarithmic equation. It's, at this point, it's linear. Get all your x's to one side. So we could minus 5x from both sides of the equation. And that'll cancel those x's on the left-hand side. Negative 7 on the left. 6x minus 5x is x. Still got a plus 12. One more step to solve for x, minus 12 from both sides. 12s cancel. And we get negative 19 is equal to x. Take out my green pen, circle it. This is the last problem I want to work through today. Problem is, this is not the answer, because you have to check. If I'm going to circle that in green and say that's my answer, move on, well, I got to check. Does negative 19 work if I put it in for x? Well, negative 19 plus 2 gives a negative number. Gives a negative number inside of a logarithm. There's no rule that says x can't be negative. X could be negative. But when you take that negative number and plug it back into the original problem, you can't have, I erased a little bit more than I wanted to. Can't have a negative number in there. X plus 2 will be negative 17. So what's the answer? Well, the answer to this equation is there is no answer. Right? There is no answer. This is no solution. 2 words. No solution. Because we followed, our rules, our laws of algebra We followed all the rules. We followed all the rules, all the laws. But the answer we got doesn't work for our original equation. Right? Negative 19 is the answer to that step. Right? Negative 19, it works for 5x minus 7 equals 6x plus 12. But negative 19 does not work for the original equation. All right, that's it. We've covered about 11, 12 problems, a lot of different types. I don't think 11 or 12 problems is enough to really get to a point where you're 100% confident with this this topic of solving exponential and logarithmic equations. But this is a good start. You know, do some homework, do some practice, and it'll start becoming more and more comfortable. All right, that's it for this video. In the next one, we're going to stick with solving equations, but solving exponential and logarithmic equations in word problems. Even more fun. All right, that's it for now. Hope this was helpful.